A very good morning to everyone. We are here today to present our major project titled A Deep CNN for Detection of COVID-19 from CT scan images. Our team comprises of Siddharth, Madhavi, Niharika, and Dedipya, whose efforts have been put together in order to make this project a success. We couldn't have done the same without the expert guidance of Dr. G. Madhu, who serves as a professor at the Department of Information Technology at VNR-BJIT, Hyderabad. The very first part associated with any machine learning project is a collection of robust data from which the model can learn and build on. We followed a similar approach in collecting and building our CT scan image data. The data has been stored in a folder named Code Test, which comprises of 3 subfolders. We have a single prediction folder which takes information and supplies it for the final prediction stage to the model once it's built. The training and validation data is stored in the folders train and val respectively. Our initial data source was collected from Kaggle and a bunch of other repositories to ensure that we were collecting CT scan images which were not just specific to the most recent COVID-19 mutation, but also took into consideration all the variants that have emerged since the discovery of the pandemic. Accordingly, we were able to collect a dataset of 1,152 images and then apply a 80-20 split with 80% of the images, i.e. 920 of them being stored for training and the remaining 232 images, i.e. 20% being used for validation and testing. Furthermore, being a classifier that we were targeting to produce, we had to label our images as COVID positive and COVID negative or normal. Hence, we took the 920 training images and segregated them into a perfect 50-50 balance, with 460 being positive samples of COVID and 460 being normal. A similar replication was also performed in the validation step, with the 232 images being split into 50% COVID positive and 50% of normal images. Once we were able to get our data set loaded and balanced, we then moved on to build our model. As you can view, we used Google Colaboratory to build our convolutional neural network. Being a high-intensity workload, we wanted to make sure that we had the best compute and GPU facilities made available to us via the Colaboratory environment. The first section of the code refers to a number of packages that were utilized by us as part of model building. Visual Keras is one such package which we use to visualize our model based on the number of layers, which will be explained later. Furthermore, we used packages such as NumPy, Matplotlib, Keras, which form the basis of any CNN model. The following cell indicates our model in terms of its constituent layers. We built a sequential CNN model that comprised of convolutional 2D layers, max pooling layers, as well as dense and flattened layers. These layers were all compiled into a single model by means of using the Adam optimizer, whose learning rate was set at 0.001 in order to ensure that our model was learning optimally from the images that were being supplied to it without any sort of overfitting or underfitting. As I had mentioned, Visual Keras was then used in order to obtain a representation of the model in terms of its constituent layers. In this image, we represent the convolutional 2D layers by the yellow sections, the max pooling layers by the pink ones, dropouts by green, flattens by blue, and dense with the dark blue shade. We then moved on to provide our model with its training and validation data. It is important to understand that a CNN model can be fed data only by means of constructing a pipeline which can then talk to the built model. We constructed a trained data generator which essentially took the images that we had stored in the train folder and rescaled them to 1/255 or 1 over the entire RGB space. We then created a test dataset out of this data generator and followed the similar labeling process as we had done in the folder structure. This gave us class indices 0 corresponding to COVID positive and 1 corresponding to COVID negative, which would then be used by the model for its prediction purposes. Once we were able to achieve the same even with the validation generator, we then went on to build our model over 50 epochs. It is important to note that we used 920 by 64 steps per epoch. This is indicative of 920 training images and 64 as a batch size for each epoch. This resulted in our model running for 14 steps in each of the 50 epochs while developing a consistent amount of testing as well as validation accuracy. Once the model was built, we then performed a simple plot over the accuracy measures and the loss measures, comparing them between the training and testing scenarios. The same is indicated here. Post this, we then moved on to feed our model with the prediction images that the model was then intended to classify. We loaded our COVID positive image from the single prediction folder and were able to then generate an output in which our built model, which we refer to as the AI over here, predicted as COVID positive. A similar sort of prediction was also run on a normal patient's CT scan image, and our model resulted in a negative prediction. The main intent of our project here is to ensure that it is capable of identifying CT scan level mutations that can then indicate whether an individual is COVID positive or COVID negative.